Hello everyone, my name is Riyaz Haque, and I'll be presenting my work on type inference for place-oblivious objects. This is work done in collaboration with my advisor, Dr. Palsberg from University of California, Los Angeles. To give a brief motivation, the paradigm of interest over here is distributed programming, and a distributed system typically consists of multiple places of computation. A place can be an abstract concept, but more likely it's a concrete thing like an MPI rank. At the bottom of it, each place has its own data store, and it can store references to itself, like to objects allocated in its own memory space, or remote objects. And invariably, local access is almost always faster than a remote access, because remote access might have to jump across process boundaries, networks, whatnot. And to tackle this problem of slow remote access, languages usually have follow two different strategies. Broadly, they are split across the lines of ease of programmability versus ease of optimization. The first one is uniform access syntax. This is something which is followed by languages like Titanium. The idea is, well, to use the same syntax for both local and remote access. Something like x.f. Now, if x is a local variable, it's just a simple object dereferencing. Otherwise, the compiler will essentially generate under the cover a remote procedure call and fetch the object at runtime. The downside with this is it becomes really hard to spot, to differentiate between local and remote access. And runtime performance can be unpredictable, because the compiler might not be able to do a good job of differentiating between the two. The other strategy is, well, let's make everything explicit. So that's where the place shift syntax comes into play. Remote access is explicitly preceded by a place shift. So you shift the place of computation to the place where the object is, and then access the data. This is good. The program can be verbose, but in the end, all remote accesses are very clearly delineated in your program, and that makes the job for the compiler a bit easier to optimize. Our work is primarily concerned with the place shift syntax, but it can be equally as well be extended or rather adapted for the uniform access syntax. So the typical thing with a place shift syntax is every time you try to dereference an object, you'll have to first perform a place check. This is like a runtime check that occurs, and if the language, if the places are equal, if the object being dereferenced actually exists on the place of execution, the execution goes forward. Otherwise, it typically results in a runtime exception. So with place checks, what is being done is we are essentially kicking the can down the runtime to discover these place bugs. And the compiler might have to conservatively insert redundant place checks, so it might make the program performance quite unpredictable. So the question to ask is, given a program, can we prove at compile time are all accesses local or not? And there has been some previous work done on this. Using static analysis, Agrawal et al. Have formulated a technique which tries to eliminate as many place checks as possible. There's also been work done in type systems. Particularly, liblit have developed a type system for distinguishing remote and local data. This is for the Titanium language. Chandra et al. Have done similar work for Extend, where they track place correlation between objects. The previous work does not tackle this one particular pattern that we found to be quite common. It's called place-oblivious objects, like we call them place-oblivious objects. In the most basic sense, the idea is, it can be seen from this example. If you see the method M, the variable x, it's immutable, it's a final field. So once it's assigned a value, we really don't care what place the object is on. We just know that it's immutable, so it's not going to change. The other thing is, we go to x's place and try to access x. This is always place safe, regardless of what the actual place of x is. So this is the pattern we call as a place-oblivious object. They can safely access other objects without the actual knowledge of their place. And as I mentioned, this is a fairly common pattern found in like 11 of the 13 benchmarks for featherweight extend. So the challenge here is, we want to type check place-oblivious objects, and our result is a type system, a polynomial, a type system for these objects, and a polynomial time algorithm for inferring the types. As for our approach, we extend Dr. Palsberg's work for the Abadi-Kadeli calculus, where he infers types for just vanilla object types. We just extend object types to places. We formulate the inference, type inference problem, convert it to a constraint satisfiability problem, and then define solvability criteria. Like eventually we prove if those criteria are satisfied, then the system is typeable, and we give an algorithm to so as to what the type is going to be. The algorithm that we have is polynomial. It has a complexity of order n cube. N is the size of the program. Our example language is a straightforward extension of the Abadi-Kadeli object calculus. We just add 3 more constructs for distributed programming. All values are objects. More specifically, they are objects extended with the place the object is on. But like standalone places are not values in our calculus. Each object, once it's created, the object cannot move around. It's just a reference to the object that can be moved around. I'll go over the concepts of like the constructs for place shift and open more explicitly later on. But here's how a rough translation of the example we saw earlier looks like in our calculus. And our final goal is we want to ensure place safety. That is, all accesses are local for any program in our calculus. The other thing I want to elaborate upon is like the actual type system. So going back to the example that we saw, if you see field F can be assigned any place. So it can be assigned, in this example, I mean, it can be assigned an object which lies on place 1 or place 2. Since x is immutable, we can just abstract that place of f from an unknown. So un kn means an unknown place. So since multiple objects are being assigned to the same reference, we don't know what the place is. So we use a specific variable called unknown to just denote that we do not know the place of computation. But for x, we know it's immutable, so we can convert that unknown to a variable x, And subsequently within the program, if we can just ensure that every time an object is dereferenced, if it has a place type X and the place of the context where the object is being dereferenced is also X, we are guaranteed place safety. So when we say like an unknown place type, it's essentially trying to forget what the type is. We don't care what the place type is. This is equivalent to using a lightweight existential type, which says there exists some place where this object exists. We don't know what the place is, but some place. And since we are using like a lightweight version of the existential types, we can actually use subtyping for instead of the pack expression that is used, that is generally used for general purpose existential types. And the typical strategy for using place-oblivious objects is first pack using subtyping, then explicitly open the object, and then access it in a place-safe manner. So this is how the syntax looks like for our language. The ones, the productions in black are standard Abadi-Kadeli calculus. The ones in red are the extensions that we have added. Particularly, the at expressions are ones used for place shift syntax. At a dot place b essentially says evaluate A, find out what place it is on, and then go to that place and then try to evaluate B. Same so for at row B. Row is just a constant place, a known constant place in this case. The other interesting one is open x is equal to A and B. So here what we say is if the type of A isn't known, then first unpack it to an immutable variable x so that we can just make it as a place constant, and then access x as a constant unknown type while evaluating B. The operational semantics look something like pretty much standard operational semantics. The only change here is we add a current place of evaluation. So we start off with a current place of execution. And the interesting thing is the case for method call or object dereferencing. We first evaluate the object to be dereferenced to a value at row prime O. So we find out that an object that we are trying to dereference is an object at place row prime, and the current place of evaluation is row. So before we actually try to dereference the object, we add a runtime check row is equal to row prime. This is the check we are trying to eventually eliminate. This is the place check, the problem in a place check. The operational semantics for place shift are fairly straightforward. Evaluate the place of A, in this case row prime, then just shift the place of computation to row prime and start evaluating B. Same so for the constant place. The syntax for open, it exactly looks like let semantics over here. In operational semantics, it makes no difference, but the big change is how we deal with it in the type rules. So as I mentioned earlier, types are again an extension of the Abadi-Kadeli object types. We just extend an object type with a place pi. Pi can be 3 values unknown, so we don't know what the place is. It can be a constant type row, or it can be a Skolem constant x, which just indicates we still don't know what the place is, but it's immutable, so it has its own place. For the purpose of this discussion, all types are finite, but the algorithm we have, it works equally well for recursive types as well. Subtyping rules, actually the third one is the most interesting. It combines the normal with subtyping with this notion of place subtyping. Even in place subtyping, the most interesting one is pi is a subtype of unknown. This is the rule that allows us to actually implement pack using subtyping. So we need not have like an explicit pack expression in our calculus. Type rules, again, the type rule is we have a set of Skolem constants, delta, a type environment, and the type of the current place of execution, and we evaluate a term, evaluate the type of a term within that context. So the interesting one here again is the method call. Given a delta gamma pi c, we first evaluate the type of A, and let's say it has a place pi. Then we add this check which says pi c is equal to pi. This is analogous to the runtime check we saw earlier. In fact, like we prove later on that if this check succeeds, then we do not need the runtime check later on. The other interesting one is the type rule for open. As I mentioned, we just evaluate A, then we unpack A to have like a constant immutable type, and that's the type of variable x, and we continue evaluating B within the extended context delta x, extended place context delta x, with the type of x, with the place type of x as capital X over here. The important thing to note here is x should be fresh, obviously. More so, the final type of the whole expression B should not contain capital X as a free variable. This is because the final evaluation of the whole expression open x is equal to A and B has B, which should be well formed according to just delta and not the extended context delta capital X. And as we see later, this condition is the one which is most challenging while dealing with the constraints. So to start, we first prove that of course the type system is sound. From a given program, we generate a set of constraints, and then we solve the constraints. The theorem we prove is if the constraints are solvable, then the program P is typable, and vice versa. Constraints look like these 5 forms. The first one is just plain object subtyping. So U and V are just object expressions. O subtype O of K, this corresponds to the delta condition we saw in the open rule. Just need to make sure that all the place values within O have to come from this set K. Each subtype H just ensures place subtyping, the rule that we saw earlier. The H element HK, this kind of restricts the choice of variables, the choice of Skolem constants or variables we have, we can assign for H. And H not equal to unknown, this is just a guard condition to make sure we always unpack an expression before we try to access it. So we cannot directly access an object with an unknown place type. So as a first step towards generating a solution, we take the closure. Closure makes all the transitive dependencies explicit in the program. The main challenge is, as I mentioned, solving the O subtype of O constraint, O subtype of OK, the constraint. We just need to make sure that like whatever value we assign for O, it has to come from all the place types in that value have to come from this set K, and that might mean that it has to go down an entire tree of other expressions. So the closure rule has to handle this case. And the theorem here is, well, a constraint set and its closure, they have the same set of solutions. Once we have the closure, we define two solvability criteria, well-formedness and consistency. Intuitively, being well-formed means if A is a subtype of B, then B at least has all the fields that A has. This is like a very standard subtyping definition. In fact, it's actually borrowed from Dr. Palsberg's work. The other criterion is consistency. Consistency intuitively means given a place variable h, there is always some value that we can choose for it. The set isn't, the set of values, the choice of values for h isn't empty. And the last theorem to prove here is if given a closed set of constraints, if it's well formed and consistent, then it's solvable. So to summarize, given a program, we generate the set of constraints, we close the set of constraints, and then we check for solvability and consistency. And if so, then the program is solvable. If not, it's not. The program is typable. If not, it's not typable. The inference algorithm is polynomial. A bit of background on the related work in this field, particularly Civil, Lahuzen. These are variants in pi calculus. They try to tackle the a similar problem of ensuring like access locality. Chandra et al. I mentioned earlier, that's work done on Extend. Although none of the prior work is actually able to tackle the concept of place-oblivious objects. The other thing is each of the methods, they use like a different method for solving constraints. The Civil is based on finding the highest upper bound. Lausanne, Chandra et al., they are based on unification. So to conclude, what we present here is a simple calculus for distributed programming, a type system with lightweight existential types. It can type check place-oblivious objects, and a polynomial time inference algorithm. And that's it. Any questions? Thank you. Yes.
Hi, interesting treatment that you have used with types, but the specific example you have used and a specific and a comment, the example you have used is definitely something that is handled well by one of the references you have shown, the Agarwal et al.'s Applas 2008 paper. It does, so what it does is it stores the place information, the abstract places, along with the object. So if you do an object.location, you get the abstract place. So as a result, if you are dereferencing it anywhere in the code, which also has the same place information, it will not have a place check. And so I agree that you are dealing with using types, which is fine. But, the specific statement you made that this example is not handled by the prior work, which is wrong, in my opinion. And similarly, you said the place, if you go back to you had shown a table, right?
Mm-hmm.
Yeah. You said the place-oblivious objects are not handled by any of the prior works. Probably you should say any of the prior works dealing with type systems.
I should have said that. That's right. That is true. I guess the primary difference between static analysis and type systems is the level of ambition. So, I agree with that.
Hi. So, if you squint hard enough, you can say that place labels are related to, say, security levels and in a lattice, and place checks are correspondingly like access checks or something. So I was wondering whether you have thought about generalizing this work to lattices, or conversely, have you looked at security type systems for object calculi and seen if your work is already subsumed by something like that in that area?
So this paper can be of independent interest. In fact, this was one of the things we did think about. I mean, if you replace places with security levels, it's the same thing. Have we gone into any existing literature? Not at this moment, but to answer your question, this work can definitely be extended to that.
Thank you. I was wondering what is the practical application that you were considering, and in particular, related question, why did you choose the Abadi-Cartelli calculus, and how does it help you with the next step?
So the Abadi-Cartelli calculus, because theoretical treatment becomes simple, the language, the calculus that we are dealing with is concise, so proving theorems, proving properties becomes simpler. We are actually working on writing a version on a working language, so it's going to be, I'm sorry? It will be Xten. So that is there, but yeah, I mean, the only reason behind choosing this was theoretical treatment becomes much more simpler with like a restricted calculus.
So you mentioned the connection with existential types several times, and there's work where existential types involve an implicit pack operation, and also we have this use of scholemized variables. So did you consider whether you could express your the checking that goes on in your language by a transformation from your language to a language that doesn't deal with these places but only uses existentials but happens to express the same constraints, such that that transform program would be type correct if and only if yours is? Basically, can you encode your constraint solving into the existential type system? Have you been thinking about that? That was certainly not obvious to me, but that makes a difference.
No. I mean, we haven't actually given much thought into that. But would you know of any particular system that actually does that?
Well, I thought it would be interesting if you could say that this place correctness property could be viewed as something that's really the same structure as what you deal with in existential type checking. Same structure, different domains.
So, well, I mean, haven't actually yeah, I mean, I would say we haven't actually looked into any other applications of these existential types in some other domain. But yeah, that would be an interesting comparison to make. I agree with that.
You did your study in the setting of place shift syntax, but at the beginning you said there are these two different alternatives. Does your work change the trade-off between the two?
It won't. I mean, so in case of place shift syntax, the check over here, the pi c is equal to pi, would be an error. In case of a uniform syntax, I mean, even in case of a uniform syntax, you still have that runtime check. There it's not a check per se, there it's like a guard condition to make sure you jump to the remote place. So in that case, it will just manifest as a warning. So, but this work is equally applicable to that domain as well.
Okay, any other questions? No? Okay, thanks again.
Thank you very much.